Okay, so today we're going to do 12.2.
Bless you. Bless you. It's July. It's July.
Let's get technicalities and get to the point. You wish to evaluate double integral over d of f of x, y, a, where d may be a non-rectangular region. All right, so in 12.1 we could only integrate over rectangles. Now we're going to expand our horizons and we're going to start to integrate over all sorts of shapes. So your book actually breaks these up into types, like a type 1 or a type 2, but I don't really care if you know what type something is, just know how to set it up. In one case, suppose D can be described as such that let me write that where I have more space to write. i.e. Right? You can describe a region such that you can say the x goes between two constants and the y goes between two functions, right? This is a certain type of region which your book probably calls type 1 or something. I don't really care what it calls it. But you should be able to recognize it. So for example, these are regions that look like, say, which one did I call? Let's say G2 is on the top, G1 on the bottom. Right, so this is an example of a possible region, right? You have some function above, some function below, but your x just goes between two constant values. Or it could look something like they could actually meet. Right, so this is G2, this is G1. And then your x goes between two values. This is your x-axis, this is your y-axis. The third way this thing could look is a case where you have something like a sideways parabola, where you'd have to actually break the function into two parts. Call this a G2 and that a G1. And we're describing this region. Right, so these are just some of the basic ways you can sort of see this idea. Right? So your y, you have a lower function and an upper function, while your x just goes between constants. You can describe a region in that way. And if I want to integrate over that such a region, then it's the same as saying putting a constant on the outside and putting the functions on the inside. remember the way your integral goes, the d's match up with the integrals. Right? So this is saying your x is ranging between a and b, your y is ranging between this function and that function. Okay. I mentioned this before, but note the setup how things work. You always will have constants on the outside, functions on the inside. Right? So here you'd have zero-dimensional objects. Here you'd have one-dimensional objects, right? Which can be described by single variable functions. If you had a third integral, you'd have two-dimensional objects, which are surfaces, which are described by two variable functions, etc. Right? So you always start with constants on the outside, and you increase the variables as you go in. So that's one way you should know if you're setting up an integral, right? You'd have to be able to set up one variable between constants, and that guy goes at the end. The next variable set up between functions, that guy goes inside. Right? And in general, f of x, y, dy, dx. What goes here is the bottom function. And the guy you write up here is the top function. What goes on here is the left constant. What goes up here is the right constant. Right? Thinking of the normal Cartesian axes, you think of x as left to right, y as top to bottom, right? So if you're looking at the shaded region, whatever shaded region is, look what's on the bottom. Whatever function that is, that goes on the bottom of the y integral. What's on top? Whatever function that is, goes on the top of the y integral, right? Look at the constants that bound the x. Which one is on the left? The a. So that goes on the bottom integral. Which one is on the right? The b. That goes on the top integral. Right? So it was from left to right, top to bottom. That's how you sort of set it up, right? So there's a left constant, a right constant, a bottom function, a top function. And you literally put them on the integral in this way, right? So once you can figure out how a region is set up, and you can actually describe it in that form, you can actually set up the integral to do it, right? So the limits on your integral actually describe the region you're integrating over. That's another important concept. It doesn't matter what the function here looks like, right? When you're setting this up, this is not what you're looking at all, right? You want to look, where am I integrating over? What region am I integrating over? This function is just something on its own. Right? But once you can figure out the region, and did someone say something? Once you can figure, what?
I just brought you.
Okay. All right. Once you can figure out your region and you can describe it in a certain way, you can set up this integral. And of course, even in Calc 2, we could switch the roles of x and y. And so we can actually do that here. We'll do some examples where we set these things up in a bit. Just right now, I just want to get the little practical theory out of the way. X and y can switch roles. And by the way, switching their roles is what we're doing when we're switching the limits of an integral. Right? In 12.1, it was easy. There were constants. You could switch them as you please. But here, it's actually a little bit more complicated. So here I could have functions like this. Like, what did I call them? G1 of y, G2 of y. This is C to D. This could be your region D, or could look something like they intersect at a point. G1 of y, G2 of y, and this can be your region D, only between C and D. Or you can have something like this. That could be your region D, where on this side you have G1 of y, you have G2 of y. Which, by the way, you can actually emphasize here that I'm talking about functions of x. Because you say y is a function of x, right, in this case. So these are all functions of x. And D is the region that you're bounding. Right? And in that case, our integral C up to D of G1 of y to G2 of y and again, so here you have the y going between the constants C and D. And here you have the x going between the functions G1 of y and G2 of y. So you can have the x go between constants and the y go between functions, or the y go between constants and the x go between functions. It depends on, well, the kind of region you have will let you know how to set it up. Let's see. Note, in general, both of them will usually work, but one will usually be easier than the other, right? Which is not a new concept. We've seen this when we were computing areas back in Calc 2, sometime thinking of it as, you know, top function and bottom function works, while sometimes you have to tilt your head and think of it as right function and left function. Or when you're doing volumes of rotation, sometimes disk washer method is easier, sometimes shell method is easier. It really depends on the region itself. So it's sort of something that you'll have to think about. But the same considerations that you had in Calc 2 when setting up a region are exactly the same ones you have here. Right? It's not really anything different. The only thing that's different here is the partial integration. So now to get that out of the way, we can do some examples. I should probably write it down so you can't say I never told you. So here, I want a description of this integral similar to how I did the description over there. So on the outside, what will happen?
The outside.
This is dx dy. So describe in words what limits you put here.
The top and the bottom.
What goes here?
Bottom.
Bottom constant, right? Emphasis on constant. Well, on the bottom also. Emphasis on everything. Right? Look at your share region. Who is on the bottom? Take the constant that describes the farthest you can go, right? And here it's the top constant. right? So remember, y, you think of going from bottom to top. It describes the vertical movement, right? As far down as you can go, tell me the constant that describes that. As far up as you can go, tell me the constant that describes that. You put it on this integral, y goes on the outside, right? What goes here?
Left function.
Left function. Right? So there's this region that's bounded by two functions. One function is on your left side, one function on the right side. The left one, write it down here. And of course, if you're describing x as a function, the variables here would have to be in terms of y's, right? It has x equals a function of y, or y is a function of x. And this would be the right function.
So what if y were the function?
Then you'd switch the integrals.
Okay.
You'd set it up as a dy dx.
dx.
Right? You will never put a function on the outside and a constant inside, ever. It's never right. If you do it, I'll just give you 0 and not even read everything else you say. Because it's just like totally.
It's another 0 moment in our lives.
It's on camera now. I've said it. I've made that decree.
I'll catch your good side while you say it.
The syllabus describes sins from your past life. No, I can tell you about sins. So in the class after Calc 3, this is one of the things where I would put in the syllabus saying, if you do this, I give you 0. This is one of those things. That's how important it is. If I see you put a function here and a constant here, it's over. Okay.
Drop the class now.
Example. Let f of x, y equal the function x, y squared. Find the integral over d of f of x, y dA if a. Now we're going to redo a bunch of examples with the same functions, but I'm going to give you different regions to practice with. So here D is the region bounded by y equals x and y equals x squared. Set this up in 2 ways. B. Let's do that example first. So I want to integrate this function over these 3 different sort of regions. And this particular one I want to set up in 2 different ways. Okay, let me set up one way, the easier way, of course. So, one thing you're always going to want to do, well, it's something you're usually going to want to do, is draw a picture, right? This is going to be, that's sort of the norm in this course. You know, a lot of times you describe a region or a surface, you'd like to have sort of a picture in your head. So y equals x squared looks like parabola. Origin. Okay. Now y equals x looks like
A line.
it's a straight line going through the origin with positive slope. Right? So the region bounded by these two functions is going to be this region. What's the intersection point? 1. 0 and 1. Now how would you find that if you didn't know? Right, so you could have find intersection by setting. Right? Intersect means they coincide. If y equals x and y equals x squared, when they coincide when x squared equals x. So we set x squared equals x, which means x squared minus x equals 0, which means x times x minus 1 equals to 0, so x equals 0 or x equals 1. And that's our intersection points, right? Now, the top function, I can describe it as y equals x, while the bottom function, I could describe it as y equals x squared, right? So I'm going to draw my picture and I'm immediately going to identify what's the function on the top, what's the function on the bottom. I've also identified the constants, right? Now my constants here are my x's and my functions are already functions of y, so functions of x. So it will be nice to set up the integral as x goes from 0 to 1, my y goes from the bottom function to the top function. And my function here is xy squared. i.e. x from 0 to 1, y is from x squared to x. Any questions on that? Let's evaluate this. How do we do it? Right, the y first. Remember, you set up constants on the outside, functions on the inside, but you always integrate the inside first. So you're going to work on this integral first, which means you're integrating with respect to y first, right? So this is your function. I want to integrate with respect to y. And what's that going to be? xy cubed over 3. This integral is there. I just left it. And this, I'm going between x squared and x. Now I just integrated with respect to y, so I'm still thinking of y as the variable. So this function that I see here, I'm going to plug into the y value, right?
So x squared is smaller in this case? Because it's less than 1? Why x squared is in the bottom?
Yes, that is correct. And if you're not sure, you can always plug in a number, right? So I know the intersection between 0 and 1, right? So I can, if I don't know who's on the top or on the bottom, I can plug in a number between 0 and 1, say a half, right? Then this y equals x will give me a half as the result. If I take y equals x squared, I'll get a quarter, right? So this one gives me the lower value, so that's on the bottom, right? So yes, that's a good question. If you don't know who's on top for sure and you're not sure how to sketch it, then just plug in test values between your intersection points. The guy who gives you the bigger values on top. Okay, so how do we finish that? So we had the double integral of d of x, y equals to, so far 0 to 1. We have x, y cubed over 3 between x squared and x. So now how do we continue? Alright, you plug in the x in the top, you get x to the 4th over 3 minus, put in the x in the bottom, so that becomes what? Becomes x to the 7 over 3. Alright, that's by the fundamental theorem of calculus, and now this is just a single variable integral. We all know how to do with those. So you add 1 to the power, divide by the new power. Go between 0 and 1. Of course, when you plug in 0, everything is dead, so you just plug in 1, you get 1 over 15 minus 1 over 24, which is, what's that? That's 15 times 24. Well, I could pull out 1/3, sure. So this is 1 over 5 minus 1 over 8. The common denominator there is what, 40?
That's 3 over 4.
So it's 8, what?
8 over
3 over 40. So it's 1 over 40.
So the whole answer is 1 over 40. Now I want to set up exactly the same integral, but in another way, right? And of course, by the other way, I mean switch the x and y, right? So here we're going to write this as dx dy. Now the important thing with that is, notice when you're setting up dy dx, your x went between functions, and your x went between constants, and your y went between functions. To switch it, you'd obviously have to describe the same region in the opposite way. Here's my region, so now I want to describe this as now I want my y to go between constants and my x to go between functions. What would the constants for the y be? Right, so you'd have to actually find the y value. Here, 1 intersects when it's 1, so y goes from 0 to 1. What about the x?
Square root of y.
The function over here is the x equals the square root of y. That is correct. The function here is x equals y. Which one goes here?
Square root of y.
The left x equals y.
Y goes here. Radical y goes there. Left, right. Always left, right. Okay? That's why I wrote that down on the integral. That's why it's at top, bottom, left, right. That's how I want you to think of it. If you look at the shaded region, who's on your left-hand side? The y. Who's on the right-hand side? The radical. Right? So then, zero to 1, y up to radical y, x y squared. Now this is dx dy. Right? So if you wanted to switch the order of integration, this is how your integral would change. It's not like constants anymore where you can just switch them and don't worry about it. Your limits will actually change when you're describing general regions. But you should get the same answer, so we can see what we get. So here we're going to integrate with respect to x first, right? So this gives us x squared y squared over 2 between y and radical y. Now x is my variable, so I'm going to plug these limits into the x. And so what am I going to get? Plug radical y into the x, you just get y, so this becomes y cubed. If I plug in just y into the x, I get, so that's just y cubed over 2. Minus, if I plug in the y, I just get y to the 4th over 2. Right? So now you just do that. So here you have y to the 4 over 8 minus y to the 5 over 20. So this is just 1 over 8 minus 1 over 10, which is what? Take out the 2 again. Okay. Okay, second example. A very rare case where you actually don't have to draw a picture because they literally just gave you the limits, so you just follow them, basically, right? So in B, this is, I said xy squared, I believe is the function. Okay, how do I set this up? dx dy or dy dx?
dy dx.
What goes out here?
Negative 2, 2, and 2x squared and 4. 4
That's
plus
4
x squared.
plus x squared. Yeah,
Wait,
that's what I wrote. Yes. 4 plus x squared. Okay, so now we just do that. Integrate with respect to y. And we see why it had to be dy dx and not dx dy, right? Because your x was the constants guy, so that's on the outside. So x matches to the outside, y is matched to the inside. Okay, so now we apply the fundamental theorem of calculus again, but now we're applying it to the y because the y was our function. So this would be x times 4 plus x squared cubed over 3 minus x times 2x squared cubed over 3. Yes?
Since x over 3 is technically constant, can you pull that out before you integrate with the dx?
Well, here I could have pulled the x out here. If that's, is that what you mean?
No, the
I mean, yeah,
Over 3.
but like before you evaluate, where you have x, y cubed over 3. Well, yeah, that's the same thing.
It wouldn't make much of a difference.
Uh,
In this case, it wouldn't make much of a difference. So what is this? What is this and what possessed me to do this, for example? So this is what? X to the 6th times 1, that's x to the 7 over 3 dx. Okay, this is going to be what? I'll need more space. This will give us what? So this is from minus 2 to 2, well, the 1/3 I can pull up. This sort of is in there all the time. So this is going to be x plus 3 times 4 squared cubed plus 12x to the 5th plus x to the 7th minus 8x to the 7th.
Why do you have a 3? Why do you have a 3 in between? You pulled out the 1/3.
Yes, this over 3 here, I pulled that out.
yeah, but
So
you're
you still have 1/3 for the second one.
Oh, right here? Yes, that shouldn't be there. So it's x to the 7 minus 8x to the 7, so I can just write this as minus 7x to the 7.
Can you do the integral like 0 to 3 and multiply?
That's what I was about to ask you. Can I?
Maybe.
Odd functions.
It's an odd function, so what does that tell you?
It's
0.
So 0.
Right. It's an odd function. Notice that all the powers of x's are odd, so if you replace x with a minus x, you get the negative of the function. So on the left side of the y-axis, you have the exact negative of as the right side of the y-axis. So they kill each other. Okay. Yeah, all those little tricks are coming back. So they'll give you a problem that looks really complicated, but when you do all the algebra out, you're like, oh, it's just 0. Okay, so you have to remember all that stuff. Part C. This was xy squared. Now part C, D was bounded by x equals y squared and y equals x minus 2. What does the picture look like?
well, y squared's parabola on the x-axis. And x minus 2 is a line. Goes through.
It's like that, right? Goes through 2. So here I'm obviously just talking
minus
about this region here. So, how do I set up that integral?
Because first we need to figure out where the intersects. The problem is line %
Sure. So how do we do that?
So equal to each other, so
Intersections. Is that what equal to? So notice here I can write x as y plus 2, right? So x equals y squared and x equals y plus 2. And I'm hoping this foils, which I think it does. And so either y could be 2 or y could be minus 1. So this is at minus 1, and this is at 2. Right? And of course, if I know the y, I can easily find the x's. Right? So the intersection here would be at, if my y is 2, then my x would be 4. And if my y is minus 1, then my x would be 1. So this actually intersects at 1. Now, how would you set up that integral?
We could do top to bottom, left to right.
What's top to bottom, left to right?
From minus the y is top to bottom.
The question is dx dy or dy dx, right? That's basically the
dy
question.
dx.
dy dx.
Oh, right, it's negative.
Yeah,
Negative,
so if
yeah.
we get the integral from the bottom limit of -1 to, so the bottom constant is -1, and the top constant is 2. Right? That's dx dy.
If you're doing dx dy, the y has to go between constants and the x has to go between functions. That's right.
Right. So then it
So
would be,
here you would have to you would describe it as y goes between -1 and 2. Your x goes between y squared and y plus 2. For dx dy, you can actually set it up this way, but you'll actually need 2 integrals. Does anyone see that?
Yeah.
Because
Because-
your top and bottom function actually changed, right? If you look at this intersection point, right? If you're on this side, your top is the parabola, the bottom is the line. If you're on this side, top is your parabola, the bottom is also the parabola, right? So your top and bottom change, which means if you're describing y as functions, you'd actually need two integrals to encapsulate, describe what this region is, right? So you'd have to describe the region between 0 and 1, right? So you'd have to have two descriptions here. You'd have to have, you know, from x goes from 0 to 1, your y goes from minus radical x up to positive radical x. And then when your x goes from 1 up to 4, your y would go from, the line would be the bottom, which is x minus 2, up to the radical x, right? So this is one of the importance of realizing how to set up these regions, knowing who do you choose to be constants, who do you choose to be functions, right? And we got that from the picture. I drew this picture and I could look at it and see who's on top, who's on bottom. And I noticed that the top and bottom actually switched on me. So it wasn't good to set up the functions to be top to bottom. It's easier to set up left to right, right? So I can see for the whole region, the parabola is on the left and the line is on the right, right? Whereas there are cases where the parabola is on top and the line is on bottom and it switches, right? So here, it's much better to set it up as a dx dy as opposed to a dy dx, even though you could technically set up both ways. One way you'd have to work harder. So I would set this up as a dx dy integral, in which case the integral would look like I want to set this up dx dy, function is x squared. So now I'm letting my y go between constants, which is minus 1 to 2, x go between functions, which is y squared up to y plus 2. So this is just x squared, y squared over 2. Take out the after here. But this is a square, so that's 4. That's to the cube, that's to the square. This other is like a 1/2 of. Now this is just 1 to the 4th minus 4/3 y cubed. That's equal to 1/2 times 2 to the 4th minus times 8 minus 1 plus that's 16. right? Jesus, I can't count you guys for arithmetic. Questions? So for the most part, I'm assuming that this stuff you guys can do, but the setup was the important thing, and knowing which way was easier, which way was the best way, and actually setting it up correctly. That's more than half the battle. The rest of it is just that.
Shouldn't that be a y equals 6?
Which one?
Second one? Second, third one? Okay. No one?
I don't think so, no.
You're evaluating with respect to x. So you plug into the x to the square, so it's going to be y to the 4 times y squared.
Oh, y squared into x squared. Yes, they should actually be y to the 6. That's right. Which means that doesn't die. See, you guys are supposed to stop me before this happens. You're just watching me like mindless drawings.
We're copying.
Okay, so what is it? You're supposed to think and copy at the same time. Okay, so this is what? Y to the 5 over 5 plus y to the 4th plus 4/3 y cubed minus y to the 7 to the 7. And now we have a lot more fractions. Thanks a lot, Kristen. It's made our life harder. Two to the 5th over 5 plus 2 to the 4th plus 4 times 2 cubed over 3 minus 2 to the 7 over 7. I'm replacing it with minus 1, so it's minus 1 over 5 plus 1 minus 4 over 3 plus 1 over 7. And that is whatever. There are actually a couple of things extra I had to say, but we're out of time, so we'll pick that up tomorrow. But the homework for 12.1 is due tomorrow. We'll finish up 12.2 and hopefully get through 12.3.